So going back to this heater example or analogy that Pete used, we talked about sound pressure sort of being the temperature equivalent. Sound power is sort of equivalent to the heater power. It's how much sound the object makes. If we were to talk about the heat flow from the heater, how heat gets from the heater to the different areas of the room, we'd be talking about something analogous to sound intensity. Where does the sound come out? You know, some areas more than others. We're going to talk about the amount of energy or watts per unit area. That's sound intensity, okay? So in order to do some sound intensity measurements, we're going to use a special device called an intensity probe, and it's going to help us extract this intensity vector from some sound pressure measurements, okay? So one of the coolest things about sound intensity is that it's a vector quantity. And so it's got some magnitude and some direction to it. Okay, it's not just a number like sound pressure or sound power. Intensity is actually a vector, so we know the directionality of it. Okay.
So sound pressure would be something like this is 50 dB, but sound intensity would be like this is 50 dB going straight up or to the left, or
exactly. Yep, magnitude and direction. If we look at the intensity as being the pressure, or that scalar pressure that we measure, and multiplying that by our particle velocity, we get force per unit area, or pressure, times distance divided by time. Follow that through the units, we get power per unit area, or watts per meter squared. Okay, so that's how we're going to be reporting our intensity. This graphic on the screen is an intensity probe, and I happen to have one here. And what we notice is that there's actually a couple components to it. Most importantly, there are two pressure microphones. Okay, so we can't measure intensity with a single microphone because we need to be able to tell which direction the sound is traveling. And so we need at least two microphones, and that's going to allow us to figure out not only the magnitude of the intensity, but also the directionality of it. Okay, and so you'll always see at least two microphones, and then this third component is this little black piece in between, and that's called the spacer. And we're going to see that's going to control the frequency over which we're able to measure the intensity with this intensity probe. Okay, so we have a special piece of equipment. Ultimately, they're just pressure microphones, but they're very highly selected, what we call phase-matched microphones, and that's going to allow us to make a very accurate sound intensity measurement.
And I got a feeling because the units are watts per meter squared, this is somehow going to let us get into power.
That's exactly right. So because we have these two microphones, it allows us to sort of see which way the sound is flowing, where it's coming from. Okay, so if you imagine these two microphones I've got here, microphone 1 and microphone 2, and if the sound is traveling sort of left to right along the slide here, microphone 1 is going to sense that pressure wave slightly before pressure microphone 2 does, right? And so if we say hits here, then it hits here, we'll call that positive intensity. And if the sound were flowing right to left across here, we'd actually calculate a negative intensity. Okay, so we can tell which way the sound is flowing, and that's going to allow us to figure out where the sound is coming from. If we move the intensity probe 90 degrees and now the sound wave is traveling up on our slide, it's going to hit microphone 1 and microphone 2 at exactly the same time, and so we call that zero intensity. Okay, so just by rotating the probe, I go from measuring the intensity to not measuring any intensity just by rotating this device. Okay. So it's very important how we hold this thing, how far away from the source. All of that's going to be very, very critically important. We have to keep that in mind. And if we hold it at sort of an oblique angle, we're going to get some intermediate answer that's the cosine of this angle. So as Pete mentioned, we can use intensity to also calculate sound power. And so Pete talked about this pressure-based method. There's also an ISO standard 9614 that is the intensity-based method. And we use an intensity probe, go test around our object, and we can calculate sound power. ISO 9614 allows us to do either of two methods. One is what they call the scanning method, where we take a measurement, we just sort of move the probe around our object. Another is called the point-by-point method. Ultimately, both of those are going to give us the same sound power number, and we're really just taking the amount of intensity measured over a surface area of our object, and we're going to multiply our watts per meter squared, or the unit of intensity, and multiply that by the surface area, meters squared, watts per meter squared times meter squared. We get watts of sound power. Okay, so let's take a look at this with a little example here. Again, we have our sound source as a speaker. We create a wire mesh around our sound source. This is going to be our surface area, and so we're going to take our microphone measurement, or our sound intensity probe, and we're going to scan continuously over this surface area for, let's say, 30 seconds. Okay, so we take one measurement, but we scan over this whole area, and we try to spend equal time at all of these different grid locations, and we'll get an intensity spectrum. Okay, we'll measure the intensity averaged over all of those grid spaces, and we'll have watts per meter squared. For our end game is to get to sound power. We would then multiply that overall sound intensity by the surface area of our grid, and we calculate a sound power number in dB of watts. Okay?
Pretty straightforward calculation.
Yeah. As long as you have the right equipment, you can get to sound power using the intensity probe. Now, obviously, if I had a more complicated sound source with multiple surfaces, I would have to repeat this measurement maybe for the top, the front, the back, the left, the right, and I'd sum all of those areas up, and that sum would be my sound power. In this case, we just have one surface, so we have one side to test. Now that's 9614-2, the scanning method. There's also 9614, the point-by-point method, which is going to take us a little bit more time to perform the test, but as we'll see here, we're going to get some more information out of it. Okay, so in this case, I'm going to measure point to point using my same intensity probe, and I'm going to go, let's say, to this upper left grid point, and I'm going to take a whole 30-second measurement. Okay, so before I spent 30 seconds scanning over the whole thing, I'm spending all 30 seconds in just that top left grid point. Then I take another measurement at the next grid point, and so on until I've taken all of these measurements, and I've got a total of 42 measurements. So I've taken 42 times as much data as I did in the scanning method. I can certainly calculate sound power, but it also allows me to do something like this, where I can now say how much sound intensity comes from which grid points, because I've got a whole measurement and I know exactly where that measurement was taken. It allows me to sort of localize where is most of the sound coming out of our sound source by drawing this contour plot. I can see, obviously, for the frequency content coming out of this speaker, most of it's coming out of this tweeter region, so it's higher frequency, much less out of this sort of woofer area. So I can say where the sound came out. Not just how much, 104 dB of sound power, but now I can also specify where. Okay, so that's the advantage of 9614-1, the point-by-point method. And this is what we would call sound source localization. Okay, I know which part of my speaker is generating the noise.